Thank you, Alexei, and I would like to thank Tobias, Roman, and Suki for the kind invitation to this work, to this very beautiful place. So, what I will do today, was asked to do a bit of a tutorial. So I'll start really with some very basic thing, but something quite fun that we realized at Tera's workshop this summer, that not many people in this audience know where the word Tera comes from. It's actually a Greek word, teras. It could signify monster. This is the closest we have, but also more like positive words like wonder and omen or something like this. So it's something you can use for next proposal. My monster yesterday night was Hyros Sinova's wine cellar. So we had invited to, if you don't know if you ever met Hyro, he's the mighty godfather of the SPICE. And he has he's a great wine connoisseur. Tonight he will probably give us a good introduction, so be at the dinner. But invite you to dinner, so it was a very good dinner, but with a lot of wine. So I hope I've managed to go through this talk. But this is the, so this is the Hercules of our days here. All right, let's see if this was true. Okay, so as a tutorial, I mean, if you really want to read what it can be done with strong Terahertz light, we wrote this review article a few years ago. It's actually been cited quite a lot, and I think we put in a lot of information about, the materials, so how you manipulate materials with Terahertz, and also how you make Terahertz light, intense Terahertz light, okay? And it's interesting, I was saying, I think at the last time I gave this talk, that this was written in 2019. There are a lot of things that are missing because a lot has happened already in the last 3-4 years. So it's a very, as we know that we work in this field, a very exciting and vibrant field. So to summarize what I wrote, the part about magnetism in that article, is there are 3 ways with which Terahertz light interacts with magnetic materials, to really make it from a broad perspective. The first one is the coupling of the magnetic field of the Terahertz with the magnetization, in this case, a ferromagnet, but you basically have the torque, okay, on the spin. The second is the coupling of an electric field that you can couple with electron phonons, electromagnets. This was the first experiment, but you basically couple to the electric dipole. And then in the magnetic material, whatever, you couple this, you can actually, if you do the right things, you can actually manipulate, for example, the magnetic anisotropy. And the last is by the heat deposited in the material. I wrote it here as a proportion to the magnetic field square because I will mostly talk about metals. And in metals, the dissipation is given by the eddy currents that are generated in the material when the field enters the material. And I will leave this out, the coupling with the electric field. So I will basically, in this talk, we discuss these 2 ways with which we can control magnetic materials. So for the first torque experiments, I mean, I would say probably the beginning of all this field with strong Terahertz was Tobias' article back in 2011 on the control of nickel oxide with the Terahertz pulses. And a couple of years later, there was a work done in Switzerland where they actually, for the first time, coupled Terahertz light with a ferromagnet. Okay, so the antiferromagnet was resonant, so you had an excitation, a spin wave excitation where your Terahertz bandwidth is. In that case, the main excitation wasn't there, so you're really driving off resonant the magnetic response, so the magnetization of the material. So, okay, so this is the first part. I will actually look, so what we did was like how, personally, I entered the field of Terahertz magnetism. And it was an experiment where we did at Stanford in the lab of Matthias Hoffmann when I was a postdoc there. And basically what we did there, we took 2 samples. One was a crystalline iron and the other was an amorphous cobalt iron boron. And what we did, we went there with a strong single cycle Terahertz pulse. And what we could observe, so if you look first on this side, that in both cases, what you have, you basically, if you can see like the coherent response to the Terahertz. So the Terahertz field look very similar to this. This is the torque. This is we measure the Mach signal versus time. And basically what you have is a response that flips signs when you flip the sign of your Terahertz magnetic field. And you see it in both cases. And if you take the difference of these two, you actually get a very similar response for this material. The difference is really you isolate the linear component, because you have, if you have the response is linear, of plus h minus h, you take the difference, you remain only with the linear response. But if you see here, in this one, in this case, there was something that was left over after the pulse went away. And this is what we saw. So in iron, there is nothing left. But in a cobalt iron boron, we could see for the first time a demagnetization, which scales as the square of the Terahertz field. And we interpreted the fact that we're basically heating up the sample. What we claim there is that the heating in this case is some sort of ultra-fast heating. You can actually, if you take the shape of the square of the Terahertz field and integrate, this curve was very noisy. We had much better data after that. You basically, you follow the shape of the Terahertz field during the demagnetization. And the steps can be as fast as 30, 40 femtosecond, and you actually see them. So that was the first evidence that we could actually demagnetize. So one of the criticisms was, okay, well, one of the claim was that if you have a pure crystalline iron, you don't see demagnetization because the dissipation is much less, but you do see it in an amorphous material. And one of the criticisms was, okay, but those are two very different materials. So can't you do something similar? And then we did. You cannot really easily make amorphous iron. So what we did, and I'll show you in a moment, is to actually study the response with cobalt iron boron or different crystalline order. Okay, but just to complete kind of this tutorial part, I mean, just to want to show another paper we did where you actually see the effect of switching the Terahertz, the magnetic component of the Terahertz field and of the DC field that you apply to your sample. So on top, you see what happens when you flip the DC field. And this is, we measure the Mach signal versus time. And you see that if you reverse the magnetic field, you basically reverse everything. So all the overall response, both the coherent response and the demagnetization, they switch field because they're both magnetic. And if you look at the long time scales, where you start to see the FMR precession, also the FMR precession changes sign, as you would expect. If you flip the Terahertz magnetic field, on the other hand, you see something similar but different. The first part, so the coherent response changes sign, as you would expect, because it's a linear torque. So you see plus h Terahertz minus h Terahertz, they have opposite sign. However, the demagnetization that goes as h square, then it has to stay the same. And this is what happens. And since it is the demagnetization that triggers the FMR, then you don't see any change in the FMR if you change the sign of the Terahertz. So this is somehow an overview of what you can do with the DC and Terahertz magnetic fields, and show you how the symmetry, and you can do the experiment to study what is interest to you. So for us, I mean, this was interesting that we could excite FMR, but the interesting part was this. So all that I show from now on will be switching the Terahertz magnetic field. And what we did, it was to study the Terahertz-driven magnetization dynamics in I don't remember now, it's 8 cobalt iron films, which we annealed at different temperature. When I say we, it means the group of Olav Helvig in Chemnitz. And so that we could have a control over the order of so we did all the characterization with the material, structural characterization, and see what happens. And we could do what you can do. So when in our lab, we usually generate Terahertz fields with these organic crystals. This is another thing that makes life easier when you want to switch the Terahertz magnetic field, because you simply rotate your crystal. It's not simply, you still need to realign a bit. This looks, when you reverse the field, it looks identical. It's not. It's very similar, but there is some tiny difference. So doing this experiment also requires a bit of care. But it is definitely much simpler than using a tilted pulse front or any generator where you are not in a collinear geometry. But with this organic crystal, it's very simple. What you see here, this is single cycle field. When we have, so this is it's a bit less than a megavolt per centimeter. So we plot this in millitesla, so 0.3 Tesla almost. What you see here are the echos from the gallium phosphide crystal, EO sampling crystal that we use. So when you do the experiment, you only have this peak. You don't have these echos. Our gallium phosphide is very thin, so the echos are very close spaced. Okay, so this is what we start doing. So I try to go, so basically the color and the scheme will be the same for all the plots. So this is a pristine sample, and we always plot plus h Terahertz minus h Terahertz. then anneal 300, 350, and so on, up to 600 C. What you see in all cases, this is cobalt iron boron, we always see the coherent response, okay? And you can isolate it again with the trick of taking the difference. If you do the difference, it looks very similar in all cases. There is some change in amplitude. I will not go too much in detail. It has to do also with the fact that the optical properties of the samples changes a bit when you anneal them. You can actually demonstrate that, this is basically the MOC that is changing. It's a bit the magnetization that changes, but not that much, but also the magneto-optical signal. But let's say, to first order, you always have the same behavior, okay, with all the samples. But as you can guess here there was very little after the sample is left, and also here, but something is happening in the middle. And that was caught our attention. So if you now take the sum of the scans that you took with the opposite magnetic field, now you see something interesting. You see basically you isolate the demagnetization, okay? And you see that the pristine sample has some demagnetization, and it keeps us, and as we anneal it, it increases down to this annealing temperature, but then it disappears almost here. So what you see here that is not going away is because, as I told you before, the plus and minus H Terahertz fields are not exactly equal. So sometimes the subtraction, the sum and the cancellation worked out very well, not here. But what is important, there is nothing after, okay? So when we reach a certain annealing temperature, there is no demagnetization. But this starting from sum, it increased to a point, and then it disappeared. So we want to look, so why is this happening? What's driving this? And this was actually quite interesting, because we tried to look at the resistivity first, as to see, and the quality of the material. And if you do, if you look at the resistivity as a function of temperature of the sample, and what we plot here in orange is the sheet resistance, so it was measured with wires. And what is plotted in blue is the Terahertz transmission, normalized. You actually see that something that happens you would expect for a system that is becoming crystalline. So you have an amorphous material where actually changes, the resistance doesn't change, up to the point where you make it crystalline, and then the resistance drops. So, okay, so this is the behavior expected for the transport property of these films. But there is no signature here of some sort of, small value, big value of demagnetization and increase. So transport alone, so if you only look at the electronic transport, you don't see any correlation with the demagnetization curves that we saw. So what could be? That's what one was surprised but interesting, and then at the end, well, we have the evidence, so I don't think there is a fundamental explanation. Well, we tried to look at different properties of the material, and what we figured out, what was kind of interesting, is that if you plot on the same plot, so this is basically the amount of demagnetizations versus the annealing temperature. So the lower you are here, the more you demagnetize. So there's a minus sign here. So if you go down, it means more demagnetization. And on the other side, you plot the remanence of the loops in the in-plane direction. So you see that actually there is the two curves mimic each other. So they are on each on their own scale. So this is just qualitative. But basically, it seems that the overall demagnetization amplitude goes as the strength of the in-plane anisotropy of the sample. So we measure, so for all these samples, we measure the in-plane loops along the easy and hard axis. And we found that the samples that demagnetize the most, the one anneal at 450 Celsius, are the ones that actually have the strong anisotropy. So they have a clearly defined hard axis, and they have a clearly defined easy axis. For these ones, with a crystalline one, there is an easy plane. And if you do, that's the interest, or the point I want to make. If you do these experiments with the infrared light, so in a near-infrared pump, we don't see any of this. So with a near-infrared pump, no matter what the crystalline structure, no matter almost the sample, you always see demagnetization. Well, the amplitude can change a bit, but with a near-infrared sample, you always see demagnetization. The cool thing with Terahertz is that somehow you actually access this information about the anisotropy of the sample, which I guess makes sense because like the energy of your excitation is quite close to the Fermi level. and you're actually more sensitive to the properties of the materials and to what happens to, in this case, to magnetotransport, I guess. So it's a fascinating thing, as we already started to see in the first paper where we had the crystalline iron and the amorphous cobalt iron boron, that you really see a different behavior with terahertz and with the near-infrared. And now we structured it and we made it more systematic. Okay, let me see. All right, so this is what I want to say. But basically, sorry, the last message about this part is that, so when we do the experiment with terahertz light, I mean, I think we need to be very careful with the material properties and the quality of the sample and the structure, because we are very sensitive to this. So if I would have shown you the curves before and told you, like, look, this is the same material, it's something that I wouldn't have expected before doing this work. Okay, so this is kind of the thing. I never show. I think this has been published now for a while. I mean, for more than a year. I mean, it appeared during the COVID time, so I never presented, but I'm happy I could show this data here so we can discuss. We don't have a microscopic understanding of what's happening. The evidence I showed is what we have. All right, let me now switch gears and to the core of the talk, which is the magnetic nutation. Is a work that we started many years ago, and it started from, I'll tell you a bit the story about this, but basically, let's start from the first part. So usually when we talk about the magnetization dynamics, we look at this equation. So for this audience, I don't need to explain it, but is the fundamental equation of magnetization dynamics. So basically, there is two terms. One is the Larmor precession. Second is the Gilbert damping. And this is, if you combine these two, this equation tells you that if you have a ferromagnet with a magnetization, apply magnetic field and in a direction which is not collinear, the thing will start to precess and align to the field that you applied, or to the effective field, which could be the applied plus the anisotropy and so on. And this is the same equation that describes the magnetization switching that we use in data storage. Okay, so what shocked me the first time I heard it, and is because I did my PhD on this stuff, and I went to a talk and someone told me, well, the LLG is wrong. And this is something that, it's not something that you accept easily, but I went reading, and I have to give a lot of credit to Jean-Éric Wegrov for this. And the reason why it's wrong is because it has an unphysical inertial tensor. And the G in the equation, Gilbert, wrote it in a footnote of an IEEE paper. I forgot to cite it here, but in a review, it says, I was unable to conceive of a physical object with an inertial tensor of this kind. So somewhere in the footnotes it was known that there was something off with this tensor. And the reason why it's off is because typically, if you remember Physics 101 mechanics, you typically have this kind of tensor of inertia for most objects. What the LLG equation assumes is that this tensor has to be with all elements 0 except 1. Okay? But if you go to your mechanics textbook, the best you can find is the rod rotating around its center or around this one edge, and is the one with two non-zero elements. So, but with only one, there is no mechanical, like classical object we can think of. And the question is, how can it be wrong? We use it. It works very well, as been demonstrated. Well, you are saved if you think that the way we use it in an approximation where it works. And if what the complete description has, that is a degree of freedom, which has a very different energy scale that you may not see, then the LLG equation is the limit of the full correct equation. And this, this is kind of recovered. So, but to say, okay, that Landau may miss something is quite scary every time I hear it, but it's actually quite interesting. This is an introduction of the volume 8 of electrodynamics of continuous media. I was talking with the chair this morning. Introduction, it says, like, in writing this book, I don't know of any other volume where it says, we experienced considerable difficulties, partly because they need to make a selection from extensive existing material, and partly because the exposition of many topics does not possess the necessary physicality and sometimes is actually wrong. We realize that our own treatment still has many defects, which we hope to correct in future editions. I mean, to credit, this was written in '59. I don't think the lasers were operating yet. But it was known that when we discuss these things, it's extremely complicated. And that's probably why we like to work with these things, because there is a lot to be understood. Okay, how do you make this right? Well, the surprising thing is that it's not that difficult to make it right. It's basically, if you do the proper derivation, you need to add an extra term to the standard LLG, which scales as the second derivative of the demagnetization. And a new constant appears, this tau. And yes, and what this equation does, compared to the LLG that has this damper section, is that it adds this notation, which for physical objects we know very well. Okay, so for mechanical objects. So it's basically as a notation on top of the precession. And you can see that this tau basically this is a bit, okay. Now the battery is a bit running out here. No, the laser is working. I can go. But basically, okay, it's the, you want to try? So it's the angular momentum relaxation time, this time is constant. So basically the time it takes for the notation to go away, and then you recover the precession. That's the idea. Okay, if you, yes, now sorry, it's a bit, yes. Okay, should go. It's much better. So if you really want to go into deep, I mean, I just showed the equation because I didn't do this, but the work of Peter Oppener, there is a way to derive this from the Dirac Hamiltonian. And actually, if you do the full derivation, you calculate the Hamiltonian for the spin, you realize that there is a term that has to go as the second derivative of the B field. Okay, so this paper is extremely nicely written. I enjoyed a lot reading it. So if you want to know more about the fundamental theory about this, it's there. So it should be there. So how do we see it? So this was, sorry, the reference is missing, but this is again from the paper of Janeri Vegro. The idea is that if you have notation, how can you detect it? Well, again, with spectroscopy. So as you measure, for example, the magnetic susceptibility as a function of frequency, we know that we expect an FMR peak, the ferromagnetic resonance peak. But if you have this notation peak, you expect to see an extra peak at a much higher frequency. When this paper was written, this is just a random position. No one knew where it was. The assumption was it cannot be slower. We would have seen it. It must be somewhere in the high frequency. And as you see, the amplitude is much smaller. So that's one reason why it may actually not been seen before. And yeah, so the story goes that in 2017, I was at the Ultrafast Magnetism Conference in Kaiserslautern, and Jean-Éric Vegro was there. And I gave this talk, and I was like, wow, this is something that I completely missed during this, in the last years. And the thing was that I realize now is wrong, but when I was a postdoc, we saw some weird oscillation in a ferromagnetic material at 0.3 terahertz. We now know this is not this one that I saw at the time. There are no notation, but it triggered me the idea that maybe that was there was something to be tested. And the idea was to go at the Telbe facility, which just started the operation, and you can actually could tune the driving, so you have a kind of narrow band terahertz field which you can tune on the low terahertz range, and you could cover this. So since there was the only data point we had, I say let's try it and then go there. So went to the Telbe facility. This is a schematic how it's made. So it's a super radiant source. So it means it's not quite an FEL, but almost for the practical purpose it is. So you have electrons accelerating into magnets that they oscillate, and then if you have the right energy of the electron beam and of the magnetic field strength, you end up with oscillation in the terahertz range, which you take away the electrons, you take only the light, and you put in a terahertz lab, in a lab where you have an optical laser synchronized with it. And then you can do terahertz pump, optical probe. And you can see you can tune the frequency. I think now they improved also, but at the time it was about from 0.1, 0.2 to 1.2 terahertz. And what we did, it was to try to see if there was this resonance. And so the first thing we started to do when we put the magnet in, it was to take, to make sure that we were doing the right experiment, so that we were checking somehow the selection rules were correct. So we put the magnetization and the H terahertz orthogonal to each other to maximize the torque, and we put them parallel to cancel it. And at least we saw that at least the signal scaled as we expected. So if you had these two perpendicular, the larger signal, and if they were parallel, there was nothing. So this, at least, we believe that we were seeing the correct signal. Let me see if I have, no, I don't have the slide, but so the way we did it, it was we had the magnetization in plane, the Terahertz in plane in the other direction, and then what we measure is the polar Mach, so it's the excursion in the out of plane of the magnetization. So you have these three torque vectors in this way. Okay, and the idea is to do a forced Lorentz oscillator experiment. So to look at both amplitude and phase of the signal. So we wanted to be before at resonance and after resonance and see, the amplitude maximized at the resonance and then lower outside, and then also look at the phase shift. That's a cool thing you can do with the Terahertz and with the femtosecond lasers. That your femtosecond laser is basically a Dirac delta, so you can sample amplitude and phase. And that's what we did. So what you show here is the K rotation at 3 different frequencies, and in gray, that's the Terahertz magnetic field, which you can reconstruct with an independent measurement. And what you see, it's already here, is that at low frequency, we're kind of in phase with oscillations. Then we move out of phase, and then even more, so 90 degrees and pi out of phase. And also, so if you look at the amplitude, you actually have a hint of a very broad. It's not well. We were hoping for a much nicer peak, but the peak is very broad. And at the time, we didn't understand why it was. So if you look at the simulation, we didn't get the right size. But I'll show you later that the mistake we made is that we assumed that the line width of the notation had to be the same of the ferromagnetic resonance line width, which is not the case. So basically, we use the same. We measure alpha with a standard FMR spectroscopy, and we put this alpha in and made a simulation. So we reproduced the peak, but not the line width. But that was, now we know that probably was not the correct approach. And yes, this is see. So the error bars is not small, but it's there. Just to tell you, each of these points is almost, I forgot, it was 8 or 12 hours of measurement. So we repeated many times. We tried the experiment 3 times, and we also jumped the frequency around, because when you have a machine of that size, the risk of seeing what the machine is doing and not what your sample is doing is very high. But at the third, and each of them is basically a week beam time to get this data point. So at the third attempt that everything was okay, then we felt, okay, now this is there. It's not a strong peak. There's a lot, the error bars are huge, but it's there. Okay. So, but what can we? But this somehow proves that there is a resonance about 500 gigahertz, which is not an FMR resonance. There are no phonons there, so it has to be something. It has to be something magnetic, and it has to be something that, it's the only idea that was put out is that there is this notation could be a simple explanation to put it there and find it. There is, just before this paper, there was another work where one potential cause, when you see this high-frequency oscillation, if you have standing waves across the thickness of your magnetic film, they can be very large amplitude, but they depend on the thickness of the film, and they are basically exchange waves. We had used films of different thicknesses, and they don't show any of this behavior. So that's why we looked into this, but that was not the case. Okay, but let's try to do more and try to understand more. How am I doing with time? Yeah, okay, 15 minutes. Okay, so microscopically, as I showed you quickly the Hamiltonian, you basically found these effects when you include higher order spin orbit terms. So the idea, very simple. I'm an experimentalist. I try to design the experiment with simple ideas. And we try to measure materials where we can control the magnetocrystalline anisotropy, which somehow is related to the spin orbit. It's not trivial, but there is some connection to it. And then this time, because the last time we measured a forced oscillation, which somehow was hiding the natural oscillation, let's try to measure in the lab with a strong Terahertz field and see where we can see the ringing, so the natural frequency of the notation. So this is what we did. So we use broadband pump. This is the spectrum, the linear spectrum of our OH1 crystal. So it's one of these organic materials that you pump with 1.3 micron, I think. And it gives you like a strong 1 megavolt per centimeter or 0.3 Tesla field at around 1.5 terahertz. Peak field at 0.3 Tesla. Sorry, was a mistake there. And then we measure with time resolved Mach, so we have a 50 femtosecond resolution, a bit better. And then we compared 3 epitaxial films. This is crucial. They had to be extremely high quality, FCC, BCC, and HCP. And so what we did, what we saw, so in this plot, I'll show you what the LLG equation without extra inertial term would give you is the response. So we take as an input our Terahertz field that we measure experimentally, and we calculate what is the response. This is simply the integral of the magnetic field. I think Tom was saying this yesterday, but it's just, the LLG is an equation that integrates the magnetic field. If you do a look at the FCC example, you see that there is a similarity. So you actually see the shape of the Terahertz. So the LLG part is integrating. There is a shift, though, and I will come back to this. The BCC looked very similar, maybe a bit smaller amplitude, but did the same. And the HCP did something quite different. I mean, again, you can see the Terahertz there, but the phase is a bit different, but it has this behavior. And what you can see here, and this is very clear, I mean, we repeated this because many times to make sure that this is there. This is real. So there is always an offset from the start of the oscillation from the time when the Terahertz arrives. In a way, this is probably the most intuitive way to see what inertia means. It means that basically the sample has some sort of inertial response inertia in itself before responding to the Terahertz field. And it's different for different materials, but here is about 400 femtosecond. But the interesting thing is even more interesting if you zoom in here, and this is an extremely tiny signal, but again, we did it many times, and the frequency is reproducible with in the different sample. It's about a signal of the order of 1 microradian, so it's extremely tiny. But you see that there is some sort of damped and quite heavily damped oscillation. And you can see it's quite similar in frequency for the FCC and BCC samples. Those are the one with a cubic structure, and it's quite different for the HCP one. So that was the evidence we saw. The other thing we did, and it's worth pointing out that at first we say, okay, can it be something else? There are no, we checked this with magnetic switch and magnetic field, everything reversed with a magnetic field, but could it be some coupling with the phonons or so on? So the first optical phonons in cobalt are at 8 terahertz. So we're very, very far away from any of those excitations. So the other thing that we did, we checked that is scaled as you would expect from this torque equation. So it should scale linear with the magnetic field, and it does. So this is, the B is just an amplitude coefficient for an equation. But basically, is the peak of is a damped cosine function, and this is B is the amplitude. And you see, for the lowest field, we have 2 microradian of Mach rotation. For the highest, we have 4, and it's a back factor 2 between them. And we can fit this quite well with the inertial LLG. And I'll show you, and one thing we did, actually, so that's, if we just fitted this, what is the damping constant, we found out that the line width is 10 times the line width of the ferromagnetic resonance. So I told you when we did the mistake in the first paper that to assume the FMR resonance was the same, then we get the too small line width. But with this, we actually, of course, matches what we saw before. And, in retrospective, it makes sense. If you have something which is a much faster process, the interaction, the dissipation that causes the damping are probably a different origin, right? So it's because the time scales are different. So assuming that the gigahertz FMR line width is the same as Terahertz notation line width, it was a bit too rough approximation. Okay, so this is just some extra data I showed there. I don't want to go too much into this, but just to tell you that the story is not over. So we can reproduce the main peak, but I'll show you that we basically now can do it with 1 input parameters. What we see, and this is something that we don't know, there is in literature some suggestion that how to do this, but you also see somehow the harmonics. It's very noisy, but it's clearly that there is some noise where we have at the multiple of the notation. So we don't know, those are not in the inertial LLG equation. They cannot be done there. There's someone proposed that if you add derivatives, you can actually do this. Yes, this could be something, the physical motivation of this, it's not clear to me yet, but it could be there. But this we don't know. So in the response, and I think in some of the curves you can actually see that there is more than one frequency. I think in, yes, you probably see it here. There is some sort of modulation on top of the peak. It's very tiny, but it's there. Okay. What is interesting, though, is that we tried to see in this paper if we could go back to the theory of magnetic inertia. So this is the inertial energy equation written by in this way by the paper of Peter Oppener, where he just changed the symbols for the Gilbert damping and the inertial term, and you have a microscopic way to derive this, and what you can see is basically where does the material dependence go in? It's here. And if you take for our sample this ratio, so we have 3 samples with 3 different oscillation frequencies, where 2 are very similar but also damping, and you take the ratio of the 2, you actually find this constant. And this is the only parameter you need to fit the oscillation. So if you go back to the relativistic theory, you take these 2 components. For the 3 cobalt samples, you get 750 plus minus 50 femtosecond is this, let's say, relaxation time that comes out of this. And this is the only free parameter you need to reproduce the evidence. So again, it's a lot more to be done, but this, I think, is a good indication that there starts to be some consistency into this. Just to show you, these are the 3 samples. So see these the 2 cubic one, this is the FCC and this is the BCC, sorry. Blue FCC, this middle one is BCC and this is the HCP. They're very, I mean, you can see that these 2 are very similar and they have very similar notation. And this is the one with a very different notation frequency. So we ask ourselves, of course, why there are so few experiments on this? Because, I mean, actually now I saw some abstract that in the upcoming MMM, there is some new groups, some other groups reporting this. But so the signal is very small, that's what I told you. So the SNR at Telve was insanely high. With 250 kilohertz laser, we actually could measure very, very tiny signal. In the tabletop, we noticed, so we tried to measure other cobalt samples. We asked the same growers to make polycrystalline cobalt samples. We didn't see anything. So to actually have high quality film seems to be essential. And in our lab, we only saw it in epitaxial cobalt films, but at least from 2 groups. Both from San Diego and the Politecnico di Milano group, the epitaxial cobalt samples. Another thing we noticed, and I'm guilty myself of this, there seems to be sometimes overlooked oscillations at this frequency and in this range in literature. This is a paper, sorry, I forgot the reference, is a technical paper we wrote for the European XFEL when we tested the new camera there to do soft X-ray experiments. And this was a cobalt iron nickel film. And we fitted, this is the XFEL data, is the black one. We fitted this with a nice exponential, and we didn't notice. I mean, I now notice that there is a Terahertz oscillation on top of that. So, and I saw some data from Herman Du's group in iron platinum where he was presented, said, look, there is something there. And it's probably very small, but they could be there, and it should be there. So, yeah, so this is, as I said, I know that I promised Tobias, but I always forget I should give you the samples to try. But I think it's good that more people measure this. But from the theory, the notation should be there. Whether it is, and we have evidence that it's at this frequency, but it could change a lot, as I said, with material property, with the sample. Okay, do I have 5 minutes left? Yeah. Okay. Look. Okay. So this is kind of that was the main topic. Now we switch completely gears, but it's something that I also want to show to this crowd because it may be interesting for some of you. Is some work we did on trying to achieve the highest possible Terahertz magnetic field using metamaterials. And so this is the people that actually did the work. And one of the way we did it was to, because there is a lot of work done to enhance the electric field of Terahertz radiation. We wanted to actually do the magnetic one. And, copying an induction stove, that's one of the best things we came up with. And the idea of this is not only the spiral. The thing that helped quite a lot, actually, is to add this arm to couple a linearly polarized Terahertz magnetic field. And this actually works quite well. So, of course, if you put 2, you would cancel it. But if you put only 1 arm, it will actually work. And what you can see This, of course, it's a large inductance with a certain resistance, so it defines quite well a resonance. So we designed them so that we had, like, by design, about 1 terahertz resonance because we want to show this. And you can calculate the transmittance, the reflectance, and the absorbance